Bismillahirrahmanirrahim. Assalamu alaikum everyone. So today we will be having our 17th lecture and we will be discussing about three-state gates in addition to problems that we will be solving. Right. So let's talk about three-state gate. Right. Actually we can have a gate, right, that can have three-state, because before we have studied the gates that can only have two states at the output, 0 or 1, right? But we can have the third state also, right? So if you look here, right, we have the input A, output X, right, and this is the control switch, right? So this is active low, right? So we can have the output as 0 and 1, but in addition to those two different states we can always have this third state, that is whenever we have E is equal to 1, right? So we will have E bar 1, right? So then we will be having a 0 here because this is the complement, right? And this inverter will act as a high impedance, or you can say this is an open circuit, right? So if you look here on the right hand side of your picture, so you can see that we have E, that is active high. Whenever we have E is equal to 0, we have the high Z, high input impedance, right? High impedance, right? So we can take this as an open circuit, right? So we now have the three states. Output can be 0, it can be 1, or we can have an open circuit, right, or high impedance. The three-state buffer, right, you can see we have the enable signal, right, input signal and the output signal. So this is whenever B is 1, right, this switch will be closed and the input will be communicated to the output, right? If we have input is 0, we can only have two different possibilities. A can be 0, so we'll be having 0 at the output. If A is 1, we will be having 1 at the output. So you can say that the input will be communicated to the output, right? And in another case, when we will be having B 0, then you can see the circuit will be, or this switch will be opened and the input is blocked, right? So this is considered as an high impedance, right? So these are four different types of three-state buffers, right? You can see we have A input, C output, and this is the control, right, input. So here B, A and C, this is the function table. You can call it a truth table. So B is 0, right, we will be having the high impedance, right? B is 0 whenever irrespective of A, the value of A, we will be having the high impedance, right, or it will be acting as an open circuit. So it means the input is not communicated to the output, right? Whenever B is 1 and A is 0, we have 0, right? B1, A1, we will be having C1, right? So in case whenever we have B1, the input will be communicated to the output, right? So here we have B, it's the same number of variables, and we have used the same names. B as the control input, A is the actual input, and C is the output. But difference is we have a bubble here that represent the complement, right? So irrespective of the values of A, whenever we have B low or 0, we will be having the high impedance, right? Or you can take it as an open circuit, right? Whenever we have B1, right, you can see that the output that has to be communicated to the the input that has to be communicated to the output is complemented. So A0, we will have C1, right, because complement, and A1 C is 0 because output will be complemented, right. So here you can see we have the bubble at the control input, that is B. So whenever we have B0, right, so it means this is active low. Whenever B0, this will be activated or it will function, right. So here you can see we have B0, right. So we have input communicated to the output. So 0, 0, B0, right, A1, and we have the 1 at the output. Similarly, if we have B high or 1, so it will be complemented and we will be having 0 at B originally. So irrespective of the input, right, we will be having high impedance at the output, or it will be acting as an open switch, right. So in other words, you can say that input is not communicated to the output whenever we will have B1. So here we have the bubble both at the output and at the control input, right. So here you can see B0, right. So we will be having input communicated to the output, but it must be complemented, right. So A0 C1, A1 C0, right. Here we have B1, right. So irrespective of the input, we have high impedance. So it means input is not communicated to the output, or it is acting as an open switch, right. So we can use three-state gate in order to design a multiplexer. So here you can see we have two. So we can use a three-state gate in order to design a multiplexer, right. So here you can see we have on the left hand side we have 2 into 1 line multiplexer, and on the right hand side we have a 4 into 1 line multiplexer, right. So if I talk about the three-state gate, right, so here I have a three-state gate, right, and again here you have another gate, right. So what will be, so if I complemented this, right, and this is the direct, right. So this is the select, right, and this is A and this is B, right, and here we have the output Y. So this is the layout of two three-state gates, right. So here you can see we have the select. Whenever select is 0, right, so it means A will be communicated to the output Y, right. Whenever we have select 1, right, it means this here we have the high impedance, or it will act as an open circuit, and here the input, that is B, is communicated to Y, right. So you can see 0, A will be selected, and 1, when S is 1, B will be selected or communicated to the Y, right. So here we have 2 into 4 decoder, right. So you can see we have I0, I1, I2, I3, right. So we have two select switches, right, and an enable, right. So whenever enable is high, right, and we have S0, S1, right, 0, 0, so 0 will be selected, right, and then we have, or you can say I0 will be communicated to Y. Whenever 0, 1, then 1 will be high and I1 will be communicated to Y, and then whenever we have 1, 0, 2 will be selected or true will be high, so it means I2 will be communicated to Y, and 1, 1, 3 will be high and I3 will be communicated to Y, right? So whenever we have S0, S1, 1, 1, right? So it means this will be high, right? So it means I3 has to be communicated to Y, and the rest of the I's, right, they will be act as the open circuit or will be having the high impedance, right? So this is the utilization of the three-state gate in order to have the multiplexer, right? So let's talk about problems. These problems have been taken from your textbook, right? So let's solve them. So here we have the problem design. We have to design a 4-bit combination circuit, right, that can take 2's complement, right? And we have to show that we can construct them by using XOR gates, right? And we have to predict the output function if we will be having 5 bits, right? Or you have to take the complement of 5 bit, right? So we will start from the 4-bit, right? So if you talk about the complement, right? So 2's complement, first we have to mention the input and the output. So here we have the 4 bits, right? And we have to name the 4 output, right? So here A, B, C, D, W, X, Y, Z, this is the input. So as we have 4 variables, so we can have 16 different combinations starting from 0, 0, 0 till we reach 1, 1, 1. This is the last combination, and this column represent the 2's complement. So let's start from 0, 0, 0, right? So if I start from this, right? So here, if I have to take the complement of 0, 0, 0, 0, right? So you know that we invert all bits, right? So that represents 1's complement. Then we add 1, right? So this is 0, 1 carry, 0, 1 carry, 0, and here we have 1 carry, 0, right? So this is 2's complement, right? So you can see we have the 0, 0, 0 over here, right? Here we have 0, 0, 0. So let's talk about 1, 0, 0, 1, right? So I will be having 1, 0, 0, 1. So first I will be inverting 0, 1, 1, 0. So this is 1's complement, right? And then I have to add 1. So this is 1, 1, 1, 0, right? So I have taken this combination, right? This one, and you can see we have 0, 1, 1, 1. So this column represent all possible combinations that a 4-bit combination can have, 4 input variables can have, and here we have the 2's complement, right? So now we have the truth table, right? You can calculate 2's complement of all the possible combinations by yourself, right? And verify. So here we have the truth table. Now what is next? Next we have to draw the K-map in order to have the simplification, right? So I have to start from, right, W, right? So first I will write down the min terms. So this is M0, M1, right, M2, M3, M4, M8, M9, 10, 11, 12, 13, 14, and here we have 15, right? So I can write 15 here, right? So these are the min terms, right? If we talk about W, right? So here you can see we have the 4x4 table, right? Mentioning the different min terms, right? So here we started from M0, M1, M2 we jump, we have a jump over here, M2, M3, M4, M5, M6, M7, right? So from here to here we have another jump, right? M8, M9, M10, M11, right? And so on and so forth. So here you can see we have CD along this horizontal direction, and then we have AB along the vertical direction, right? So now we have to map. For W, you can see we have 1 at M1, right? M2, right? This is M2, then M3, M4, right? M5, M6, M7, and we have another one at M8, right? So all other are zeros, right? So now we will be looking for the groupings. First we will look for quads, right? So there is no quad, right? Because in case of quad we have the maximum possible simplification, right? So we look for groupings in order to have simplifications, right? So then after the quad we will look for a square. So here you can see we have a square here, right? So as a result of this square we have a term, right? And then we have another grouping of 4 ones, right, here, right? And then we have another grouping of a pair here, right? So this is the only one, right? So as a result of this one, you can see we will be having the term with 4 variables, literals, right? So here we have A, B bar, C bar, D bar, A, B bar, C bar, D bar, right? So as a result of this one we have this, right? And then for this square we will be having what, right? We have A bar, right? And C will be eliminated, right? So we will be having D. So A bar, D. So this will be the term A bar, D, because A bar has been taken as common, right? So as a result of this, right, this horizontal group of 4 ones, we will be having A bar B, right? A bar B, right? And then for this pair, right, this one, we will be having what? We will be having, right, A bar B bar, right? And we will be having C, right? A bar B bar C. So after the simplification you can have A, this is what? This is XOR B plus C plus D, right? So this is the final expression, as here we have already mentioned that we need to use XOR gate. So this is the XOR gate, right? So now we will be doing the same for X, right? So you can see we have 1, M1, right? M2, 1 here, M3, 1 here, right? M4, and then M9, M10, M11, right? M12, right? So you can see we have M12 here, and the rest of the output for X are 0, right? So now what we will be doing, we will be simplifying. So we will be looking for different groups. So here you can see we have a pair here, right? Then we have a square here if I bend, right? So I will be having M1, M3, right, along with M9 and M12 as a square, right? So I can reuse those ones, M3 and M11. So I will be having another square after bending, that is M2, M3, M10 and M11, right? So after those groupings, then we will be having the simplified expression, right? So here you can see we have B XORed with C plus D, right? So this is the expression for X. You can reach here after some arrangement of Boolean terms, right? Then we will be looking for y, right, or mapping y onto the k map, right. Here you can see we have m1, m2, right, and you have a very interesting similarity over here, right. So I have 0 1, right, if you look here, right, and then 1 0 0 1 0 0, right. So you can see we have m1 m2, so 1 1 2 zeros 1 1 2 zeros 1 1 2 zeros 1 1, right. So here you can see m0 m1, right. So after that we have m2 m3, right, right, 2 1s 2 zeros, right. So then after that we have m3 0 m4 0 m5 and m6 2 1s, right. So then we have m7 m8 0 2 1s m9 m10, right. Then we will have 0 at m11 m12 0, right, and finally we have 2 1s m13 m14 and m15 is 0, right. So you can see we have a group of 4 here in this column and a grouping of 4 1s here in this column, right. So as a result of this, right, so we will be having C D bar, right, and for this we have C bar D, right, and for this we have C D bar, right. So you can see we can replace this, or this is equal to C XORed with D, right. Right. Finally we will be having the K map for Z, right. So you can see for Z we have another pattern, right, 0 1 0 1, so till we finish here, right. So 0 1 0 1 0 1 0 1, right, 0 1 0 1, right, then 0 1 0 1, right. So we have a quad here, right, because we have the maximum possible simplification by having the quad, right. So you can see we have a quad here, and as a result of this quad we will be having D only, right. So because C bar C, they will cancelled out, right. So and here we have the, so if I have to calculate this, right, so let me solve this. So here we have so let me start here, A bar B bar, right, plus A bar B, right, plus AB plus AB bar, right. So that will be multiplied with, because this will be the, so here we have C bar D, right, plus CD, right. So they will be multiplied. So if I have to, so what I can do, I can take A bar as common, so B plus B bar, right, plus A common, right, so B plus B bar, right. So if A, this is 1, so this is B plus B bar, and A bar, and this is 1 again, right. So this will be 1. So here, from here I can take D common, right. So I will be having C bar plus C, right. So this will be 1. So I will have to multiply this with D. So A plus A bar 1, so I will be having D only, right. So we have the D only as a result of this quad, right. So this is the solution of the problem, right. So another question was how we can have a 5-bit 2's complementer, right. So here is the expression, Boolean expression, we can verify it. So we will be having E XORed with A plus B plus C plus D, so this will be the 5's complementer, and we have an additional variable E, right, because A, B, C, D, they are 4 variables, and we have to introduce another 5th variable in order to have a 5-bit 2's complementer, right? Okay, so you can verify it, right? So let's have another problem. We have to design a 4-bit combinational incremental circuit, right? So like if we have the input, right? So here is the circuit. We have 4 half adders, right? So if you talk about the half adder, right? So here we have the half adder that can handle 2 bits only, and we have the 2 output, one for sum and the other one for carry, right? So if I go back, so these half adders are connected in this way, right? So these are the 2 inputs, right? This is sum and this is carry, and carry is connected to the next half adder, right? So this is one of the input of the half adder, right? So here again we have a sum and a carry. Again carry is connected to the next input of the half adder. So here you can see we have the circuitry, right? So now we will be verifying if we have to increment, right? So let's start with, so if I will be having 1 here, 1 here, 1 here, right, and 1 here, right? So I can take this as 0, right? So 1 1 1 1 1 1 0, right? So what will happen? See, half adder can add 2 bits, right? So 1 0, sum is 1, right? So we will be having a 1, right? And then this is the carry is 0, so that carry will be here, right, communicated here, and we will be having a 0 here, right? So 0 1 1, right, and then carry 0, right? So we will be having a carry 0, right? That 0 will be communicated here, right? So 1 0 1 0 carry, right? So I will be having another 0 here, right? So sum 1 carry 0, right? So what will we have? We have 1 1 1 1, right? That should be the answer, right? Because we have to increment, right? So here if I talk about the addition, right, 1 1 1 0, and I have to add 1, so what will be the answer? 1 1 1 1, and you can see we have the same answer, right? So let's talk about if I have a 1 here at 0, right? So I will be erasing this, right? So let's have a 1 here, right? So what will happen? So we have 1 1, we will be having a 0 here, right? I will be writing here 0, so I will write from by using this mouse, right? So 0 here, right? And then 1 carry, right? I will be writing here 1 carry, that 1 carry will be moved here, right? So 1 1 0 is sum 1 carry, right? And then this one will be moved here, right? 1 1 0 sum 0 and 1 carry, right? And then we have the same one here, so 1 1 0 sum 0 and 1 carry, right? So what will happen if I have the same, right? So 1 1 1 1, I have to add 1, right? So 1 0 1 carry, 1 1 0 1 carry, 0 1 carry, 0 1. So this is the verification. So we have designed a 4-bit combination circuit that can increment, right? So we can increment 1, right? So now we have to design, this is the B part of the same problem, a combination circuit that is decrementing, right? So it means it has to subtract a 1 from a 4-bit binary number, right? So here what we have done, we have half adder, right, at the input, right, and here we have the full adder, right? So here you can see that we have mentioned the difference borrow, right? So this borrow is connected, because if you talk about the full adder, right, so this is the full adder, right? For a full adder we have an input carry, right, 2 input bits, right, and a sum and a carry that has to be propagated, right? So here you can see we have half adder, right, because we have no carry when we start, and then after we have borrow, right? So actually what we need to do, we need to add -1 in order to have a decrement, right? So here you can see we are talking about the adders, but what we need to do, we need to add -1, or you can say that we have to take the 2's complement, right? So this is the full adder, right, and you can see we have cascaded 2 half adders in such a way that it represent a full adder, right? 2 bits, right, 2 input bits, this is the input carry, and this is the sum, and this is the carry out, right? So here we have a 4-bit circuit that can do addition and subtraction. If E is equal to 0, we will be adding. If E is equal to 1, the bits will be subtracted, right? So this is the idea or tip how we can do or solve the problem which we mentioned over here, right? So we have to take the 2's complement, and then we have to add -1, right? So here we have another problem, right? We have to compare 2 4-bit number, right? Okay. And we have to check either they are equal or not, right? So you can see that we have the XNOR in order to compare 2 bits, right? So if if I talk about XNOR, right? So we have normally have XNOR, right? So we have the expression AB plus A bar B bar, right? So you can see if I have A is equal to 0, B is equal to 0, right? So what I will be having? I will be having 1, right? And if A is equal to 1, B is equal to 1, again I have a 1. If I put A is equal to 1 here, B is equal to 1 here, right? So if I have A is equal to, so this is the another possibility, A is equal to 1, B is equal to A is equal to 0, B is equal to 1, right? So if I put here, right, you can see we will be having 0, right? And if A is equal to 1, B is equal to 0, I will be having 0 again, right? So these are the possibilities when we have both A and B equal, right? And these are the 2 possibilities where we have A 2 bits are not equal, right? So this is the logic, right? So you can see we have the comparator for individual bits, right? We have to compare 4-bit number, so we have to compare A0, B0, the corresponding bits, right? So if I write in this way, right, A0, A1, A2, A3, right? B0, B1, B2 and B3. So you can compare this with the help of XNOR, right? So let me call it or name it XNOR. 0, right? So I can compare this, right? X nor 1, I can compare this with the help of X nor 2, right? And I can also have X nor 3, right? So here you can see we have 1, 2, 3, 4 X nors, right? And they are comparing the corresponding bits, right? A0 is compared with B0, A1 is compared with B1, and A2 is compared with B2, right? And A3 is compared with B3, right? And their output is ANDed, right? So if all the 4 bits are equal, so we will be having a 1 here, so it means the 2 numbers are equal, right? If any one of the corresponding bits, right, they are not equal, we will be having a 0, right? So this is the philosophy or logic behind this combinational circuits, right? So that we have to compare the corresponding bits at each position, right? So this is the Boolean expression. You can also have the idea, right? So you can see that here we have ANDed all those different XNORs, right? So this is A0 XORed with B0 complement, A1 XORed with B1 complemented, A1 XORed with B2 complemented, and they all are ANDed, right? So this is the AND gate representing the output, right? So let's move to another problem. We have to draw the logic diagram of 2 to 4 line decoder using NOR gates only, right? And we have to introduce an enable input in order to have more control. So here you can see we have 2 inputs, right? Because we have to design a 2 to 4 line decoder. So here 2 inputs, A0, A1, this is the enable. So you can see we have D0, that is equal to A1 plus A0 plus E bar whole complement, right? So if I represent this with this, so we have to break the line, change the sign, break the line, change the sign. So here A1 bar, right? So this is OR, and here we have the AND, right? So then we have A0 bar, right? And double complement over E will be cancelled, and we have E only, right? For D1 we will be having this, for D2 this, and D3 this one, right? So this is the logic diagram of a 2 to 4 line decoder, and we have used NOR gates only, right? And here we have another problem. We have to use a decoder and some gates in order to design a combinational gate, right? A combinational circuit that is defined by following 3 Boolean functions, right? F1 here, y bar z plus x z, F2, right? F3, right? So this is y bar z. So if I have a pair here, so because you can guess that we have 3 inputs, so I can draw a truth table, right? Starting from 0, 1, 2, 3, 4, 5, 6, 7, right? So for y bar z, you can see we have a pair here, right? And then xz, right? So it means this is xz, because y is eliminated here as a result of this pair. So if I have to represent this in terms of min terms, right? So you can see we have a 1, right? Then we have 5 and 7, right? So then we will move to F2, right? For F2 you can see we have y bar z bar, right? So and x y bar and y z bar, right? So if I talk about y bar z bar, right? Y bar z bar, right? So this is y bar z bar, right? And that is right? So this is y bar z bar, right? So here we have x So you can see those two pairs, they are mixed with M2 and M6 in order to have a square, and we will be having only Z bar, right? Okay, so if I have to write the min terms, so you can see we have 1 at 0, M0, then M2, right, 2, and then 4, 5, and 6, right? Okay, and then I will be having the map for F3, right? Here you can see X bar Z, so X bar here, Z, right? So this is this pair, and then YZ, right? So where is YZ? So we have a YZ over here, so those ones, right? So you can see we can represent this in terms of by using min terms. So M1, 3, and 7, right? So now we will be having this circuitry, right? We can see we have a decoder, that is a 3 × 8 decoder, because the input variables are 3, right? And we will be having 2 raised to power 3, 8 different output, right? So we have to use a decoder. So this is 3 × 8 decoder, or you can say binary into octal decoder. So these are the 3 inputs, and these are the 8 different outputs, right? So you can see X, Y, Z, and we have inverted the so we have started from here 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, right? So the so we have to use a 3 × 8 decoder, or you can say a binary to octal decoder. So we have this is the most significant bit, right? And this is the least significant bit, right? And you can see that we have inverted the order, right? So here we have 2 raised to power 2, 2 raised to power 1, 2 raised to power 0, so Z, Y, and X, right? So what we have to do, we have to odd the for F1 1, 5, and 7, right? This is F1. You can see we have 1, and then we have 5, and then 7. They are odd, and we will have F1. For F2, 0, right? So this is 0, and then 2, and then 4, and then 5, right? And then 6. So you can see that we have 1, 2, 3, 4, 5 different inputs that are odd, and we are having F2, right? And for F3 we have 1, right? 1, 3, this is 3, and then we have 7, right? So this is the F3, right? So now we have represented those Boolean expressions by using a 3 × 8 decoder, right? So we have another problem, right? We have to construct a 16 × 1 multiplexer with two 8 × 1 and 1 2 × 1 multiplexer, right? So we can use the block diagram. So here we have 8 × 1 multiplexer, and then we have another 8 × 1 multiplexer, and this is 2 × 1 multiplexer here, right? So you can see we have S0, S1, S2, S3, right? These are the switches, right? Control switches, you can say, and you can see we have used 3 of these S, right, in order to control 8 × 1 multiplexers, right? So here we have S0, S1, S2, right? So they are straight away joined to S0, S1, S1, S2, and for the second one the same, S0 is connected with S0, right? So these are the switches in order to control. Now what we will be having, right? So here we have to select one of the multiplexers. So whenever we have S3, right, is 0, right? So it means what will be having? We will be, so 0 0 0 0, right? So it means this will be selected, right? And whenever we have S3 1, right? So you can see that 1 will be selected, right? And you can see if I write down the combinations, right, for S0, S1, S2 and S3, so 0 0 0 0, right, 0 0 0 1 1 0, right, then we have 1 1, right, 1 0 0 0, right, 1 0 1, right, 0 1 1 0, right, 0, and here 1 1 1, and here we have 0, right? So I move here. So here you can see that I will be having a 1 here, right? If I number them 0 1 2 3 4 5 6 7, right? So those 8 are selected when we have a 0 here, right? So it means whenever we have 0 at S3, this multiplexer will be selected, and when we have 1 over here at S3, right, if I name them as S3 here, right, S3 here, right, and S2, and this is S1, and this is S0, right? So whenever we have a 1 here at S3, then this multiplexer will be selected, right? Right. So we have constructed a 16 into 1 multiplexer, right? And we have used 3 multiplexers, 2 8 into 1, and then 1 2 into 1 multiplexer, right? Okay. This is another problem. We have to implement the Boolean function with a 4 into 1 multiplexer, and we can also use some external gates, right? So here this is the Boolean function that we have to implement, right? So you can see we have A, B, C, D, right? So these are the inputs because we have 4 variables for inputs, right? So 0 0 0, we will start from 0 0, and we will have all the possible combinations, right? So you can see we have AB, right, is equal to 0 0, right? F is equal to D, right? So here if you look at D and F, they are the same, right? And AB is equal to 0 0. AB, whenever we have AB is equal to 0 0, right, 0 0 0 0, all ABs are 0 0, F is equal to D. When AB is equal to 0 1, right, so we have made the classes, right? So for AB we have 0 0, AB 0 1, AB 1 0, AB 1 1, right? For AB 0 1, we have F is equal to C bar D bar, or you can say this is the NOR gate, right? For AB 1 0, we have CD. For AB 1 1, F is equal to 1, right? So you can see we have this NOR gate, right, with CD. This is the AND gate, right, with CD again, right? And here is the output. So this is the 4 into 1 multiplexer, and we have implemented this. So now we have to implement this Boolean expression, right, and we can use external gates, right? So here you can see we have again different classes, right? AB 0 0, AB 0 1, AB 1 0, AB 1 1, right? So if you look here, whenever we have AB 0 0, right, we have F is equal to C bar D bar. This is the XOR gate, right? And whenever AB is equal to 0 1, so this is the XNOR, right? C bar D bar plus C D bar, right? So if I have to take the min terms, right? So you can see that we have C bar D bar here, right? And here C D bar. So we have to, if I have to draw the min terms, so I'm considering CD, right? This is the input and this is the output. So C bar D bar, and here we have another one, CD, right? So for AB is equal to 1 0, we have all ones, right? So it means F is equal to 1. and for AB is equal to 1 1 we have F is equal to D. So this is F is equal to D, right? So you can see we have the multiplexer, 4 into 1 multiplexer. These are the inputs that are attached to these control switches, right? So these are the external gates which we have used. So first we have C bar D bar and C bar D C D bar, right? So this is the C D bar and C bar D, right? And this is the XNOR, right? This is connected to the, whenever we have 0, this is 0 0, this is 1 2 3, right? So 0 0 0 1 2 3, right? So you can see that for this we have connected the output of this XOR gate to 0, and then this XNOR is connected to 1, and then we have for 2 we have 1, right? For 3 we have D, right? So here D is connected to 3, right? So this is the implementation of this Boolean function, right? So let's have another problem. We have to design an 8 into 1 multiplexer, right? That has inputs A, B and C, right? And we have 3 switches, right? Selection switches S2, S1, S0, and the data inputs are I0, I2, I3 until I7, right? And the values of those different data inputs are I1 is equal to I2 and I7, they are zeros. I1, I3 and I5 is high 1, right? And I0 is equal to I4, and this is D, and I6 is D0, right? So we have 3 different inputs, right? And you can have an idea. So it means 8 into 1 multiplexer, right? So we have to introduce another D, right? And here you can see that this is not looks like a truth table. You can say that this is a function table, right? So here you can see we have for I3 is equal to 1, we have those combinations, right, for A, B, C, D, right? And we have output F11. For I5 is equal to 1, we have those combinations, right? And we have F is equal to 1 1, right, for I0, and so on and so forth, right? So we can summarize that other minterms are zeros, right? So here we have the K-map, right? So you can see we have M1, right? If I look here, this is the M1, right? And then we have M6, right? M7, M9, M10, 11 and 12, right? And you can see we have some pairs, right? And these are the minterms 1, right, 6, 7, 9, 10, 11 and 12, right? And this is the similar, right? So here you can see we have another function table, right? And we have to map this, right? So this is the mapping, and you can have the grouping after the mapping, right? And then we have the simplified Boolean expression, right? And that's all for today's lecture. And today we have discussed about 3-state gates, right? And we have solved some of the problems from our textbooks. So that's all from my side. Apna ख्याल रखिएगा. अस्सलाम वालेकुम.